I'll be presenting our paper, Extensions of Karga's Algorithm, Why They Fail in Theory, and How They are Useful in Practice. Karga's algorithm is a fast, but also an extremely simple method for finding minimum cuts in graphs. Just as an illustration how simple Karga's algorithm is, here's an implementation in pure Python and barely over 10 lines of code. Now, Karga's algorithm solves the global minimum cut problem, and we'll get to what exactly that is in just a second. But there's also a closely related problem called the stmin cut. It's arguably even more important. For example, it appears as a building block of larger machine learning pipelines in many different areas, from image segmentation to natural language processing. But even beyond that, it's also an extremely important problem in computer science more broadly. Now, on the one side, here we have this extremely elegant and successful algorithm, and on the other side we have this extremely important problem, which is basically just a close variant of the global min cut that Karga's algorithm was designed to solve. So a natural question is, can we somehow extend Karga's algorithm and use its success for the stmin cut problem as well? But before we get to that, we first need some background, and we'll start with what minimum cuts are, or more precisely the global minimum cut problem that Karga's algorithm solves. We are given a graph like this one, and we want to separate the vertices of that graph into two disjoint groups. We do this by cutting edges of the graph, and our goal is to minimize the number of edges that we have to cut. So in this example, we could simply cut the edge at the top here, which would already split the graph into two disjoint parts. Now, we can also define this for weighted graphs with positive edge weights. In that case, we simply want to minimize the sum of the weights of the edges that are being cut, rather than just the number of edges. Okay, so how does Karga's algorithm find such minimum cuts? If we are given a graph like this one, our first step is just to select any edge at random. For example, here the one between B and C. And again, this also works for weighted graphs. In that case, we choose an edge with a probability proportional to its weight. As a second step, we then merge the two nodes connected by that edge, or we also say we contract the edge. And then we may get some parallel edges like here, and we can simply combine them into one heavier edge. And now we just repeat this procedure. So what that means is we again select an edge at random, for example the one here in orange, and then we contract that edge. And we repeat this process until we are left with a graph that only has two vertices, like in this case. And once that's the case, we stop this contraction procedure and instead cut the remaining edge between these two nodes. And that gives us a cut of the original graph. So in this case, we have the minimum cut we've just seen, with A on one side and B, C, and D on the other side. Now, of course, this is a randomized algorithm. We've made all these random choices of edges. So in general, we are going to get different cuts each time, and they might not be minimum cuts. But the crucial property of Karga's algorithm is that it produces a minimum cut with a probability of at least 1 over n squared on a single run, where n is just the number of vertices in the graph. What that means in practice is that we can use this algorithm and just run it a bit more than n squared times on the same graph, and then we're going to get a lot of different cuts. And if we pick the best one out of all of those, then it's very likely to be a minimum cut. Now, we've seen the global minimum cut problem and how Karga's algorithm can solve it. Let's talk about the stmin cut. It's very similar to the global minimum cut problem. We still want to separate a graph like this, but now there are two special vertices, S and T, and our cut needs to put them on different sides of the graph. So, for example, we can't just cut the edge at the top anymore, because then S and T would both be on the bottom side of the cut. Instead, for example, we could cut these two edges, which would be one stmin cut of this graph. Now the question is, can we somehow extend Karga's algorithm so that it finds these stmin cuts? And it's indeed very easy to modify Karga's algorithm such that it always separates the seeds like this. But our main theoretical result is that we won't get a polynomial success probability like this 1 over n squared we had before. More precisely, we define two very large and natural classes of extensions of Karga's algorithm. We call them continuous contraction algorithms and local contraction algorithms. And we then show that for any algorithm in either of these two classes, there are some graphs on which this algorithm finds an ST-min cut with only exponentially low probability in the number of nodes. So what that means is we'd have to run this algorithm an exponential number of times to get a high probability of overall success. And of course, that makes the entire approach impractical. So extending the Kargas algorithm to the ST-min cut problem doesn't seem promising, but we don't have to stop here. Especially in machine learning, we're not always interested in finding minimum cuts necessarily. What we care about is maybe performance in some downstream task, and for that we just want good segmentations in some vaguer sense. Now, as I said, it's very easy to adapt Kargas algorithm so that it always separates the two seeds. So we could just sample a cut using Kargas algorithm, which separates the seeds, and then use that as our segmentation. But of course, that's very noisy, and it might not produce a good cut in many cases. So what we can do instead is just run Kargas algorithm a bunch of times on the same input graph. And because it's a randomized algorithm, this is going to give us this ensemble over different cuts. And then, if we want to decide for some node V, for example, here highlighted in gray, whether it should belong to the red class or the blue class, so to the seed S or to T, we just count in this ensemble how often it occurs on each side of the cut. So in the example shown here, V belongs to the red side of the cut 5 times and to the blue side only once. So we would estimate the probability with which Kargas algorithm assigns V to the red side of the cut as about 5/6. And of course in practice we could do this with much more than just 6 runs, but the principle remains the same. Now we can repeat this for each of the nodes in the graph, and then we get this probabilistic assignment over all the nodes in the graph and all possible classes. In this case we only have 2, but there could be more. And then we can either use this probabilistic assignment directly in some downstream task, or if we need a hard assignment, we just assign each vertex to the seed to which it is most likely to belong. So essentially we round these probabilities to 0 or to 1. Now, this probabilistic assignment is very reminiscent of the random walker, which also takes in a graph as input together with some seeds, and then produces such an assignment for each node and each possible class. And in fact, the theoretical similarities between the random walker and Kargas algorithm are much deeper than that. We can interpret both of them as forest sampling methods. So, for example, in the case of Kargas algorithm, instead of thinking about it as sampling cuts of the graph, we could also think of it as sampling spanning forests of the graph, and then these forests induce the cuts that we usually see. And viewed under that lens, the only difference between the random walker and Kargas algorithm is the distribution over forests that they sample from. So in the case of the random walker, it implicitly samples from a distribution over forests where the probability of sampling a forest F is just proportional to the weight of that forest, so the product of all the edge weights. Whereas for Kargas algorithm, it samples from a distribution over forests that also contains this term, but then has this additional dependency on the topology of the forest and of the entire graph. And in our paper, we argue that this additional dependency should make Kargas algorithm, or the seeded version that we use, more confident in some sense than the random walker. So it should assign probabilities for each node in the graph that are closer to 0 or to 1. And in fact, that's exactly what we observe empirically. So in this example, we have an image on the top left, and we can get a graph from that by using each pixel as a node and connecting neighboring pixels using edges. And then we can apply Kargas algorithm, or the seeded version of that, and the random walker to this graph. And this gives us a probabilistic assignment for each pixel, whether it belongs to the foreground or the background. Now we also have this beta parameter that simply describes how exactly we compute edge weights from the image. But if you look in each of the columns where we only have a single fixed value of beta, then you can see that in each instance, Kargas algorithm produces an assignment of probabilities that's much more confident. So all of the probabilities are closer to 0 or to 1 than for the random walker. We then also benchmarked Kargas algorithm against the random walker and other methods, first on an image segmentation problem like this one, and then also for semi-supervised classification. And in all of our experiments, Kargas algorithm performs at least as well as these other methods. It's also very fast asymptotically. The runtime is just linear in the number of edges. So in conclusion, we've shown theoretically that it's not possible to successfully extend Kargas algorithm to the ST-MinCut problem. But on the other hand, if we use the ensemble over cuts that it generates, then it is useful for segmentation viewed more broadly.